So we were discussing why supersymmetry. And what we discussed was that how, unlike gauge theories with fermions and with no elementary scalar fields, all parameters in such theories are natural, which means there are approximate symmetries associated with those parameters. But theories which have elementary scalar fields, interacting elementary scalar fields, the mass of such a scalar field is not a natural parameter because there is no approximate symmetry associated with it. What does that mean? That means that the masses of elementary scalar fields, because they receive chordally divergent corrections, radiative corrections, they are not stable under radiative corrections, which means if you have any other mass scale in your theory, have heavier mass particle, fermion, scalar, gauge field, or whatever you have, or any other new scale of interactions, that will feed into the low mass and drive the low mass to the highest possible value. And so the scalar mass is radiatively unstable. So let me discuss this issue of naturalness in electroweak theory. Electroweak theory. For a good reference of recent reference on electroweak theory, I don't know if I have given you this article earlier. There's a review article by Gautam Bhattacharya. I always have a problem of how to spell Bhattacharya. Sometimes there are two Y's, sometimes there are two R's. So Gautam Bhattacharya, and the title of the article is A Pedagogical Review of Electroweak Symmetry Breaking. Scenarios. It's published in, where is it published? Reports of Progress of Physics. Reports, Progress, Physics. 74, volume 74, 2011, 26026-201. What I'll do is that I will not discuss electroweak theory, which is SU2 cross U1 theory, but I'll discuss a simpler prototype of electroweak theory, which has all the features of electroweak theory, but is simpler to present. What I'll discuss is a U1 gauge theory, local U1 theory with spontaneous breakdown of gauge invariance. The theory will contains a U1 gauge field, A mu, charge scalar fields, phi, which is complex, charge scalar field means complex, phi, charged left-handed fermion, charge under this U1. left-handed L, and charge neutral or neutral right-handed fermion. So we'll have the gauge couplings of the left-handed fermion to photon, to the gauge field, U1 gauge field, because it's charged. There will be no couplings of the neutral right-handed fermion because it's not charged, so it will not couple to gauge field. And there will be also Yukawa couplings with so these are the features of standard model of electroweak theory. You have gauge fields, you have left-handed fermions, which are gauge doublets, SU2 left doublets, and you have right-handed fermions, which are SU2 singlets, and then you have Yukawa couplings. So this theory has similar features as electroweak theory. The Lagrangian density that we'll use is, Lagrangian density for this theory is -1/4 F mu nu square, that's for the U1 gauge field, plus the fermion action for the left-handed fermions, I psi L bar gamma mu d mu minus I e a mu psi L. Because psi L is charged, so it has coupling to gauge field. E is the U1 gauge coupling. So psi 1 is unit 1, charge unit 1 or -1. And then the kinetic energy for scalar field, d mu plus I e a mu phi star d mu minus E a mu phi. That's the kinetic energy for a complex scalar. E electromagnetic coupling -1 as the unit of charge. And to this we add some potential. Potential is mu square phi star phi minus lambda phi star phi square, aquatic potential. And then we add Yukawa couplings. Y is the strength of the coupling times phi psi left psi r, psi bar left psi r, plus phi star psi r bar psi L. Phi has unit 1 charge, psi bar has unit -1 charge, so this is an U1 invariant object. Similarly, phi star has -1 charge and psi L has +1 charge, so this is a U1 invariant coupling. So this is a Yukawa coupling. Yes. Yeah, so let me explicitly write. This theory has invariance, U1 invariance, is that A mu changing to A mu plus 1 by E d mu theta phi or A mu prime equal to this. Phi prime is exponential I theta phi and psi L prime is exponential I theta psi L and psi r prime is same as psi r because it is neutral under U1 charge. So like I said earlier, It has all the features of electroweak theory. It has gauge couplings, it has a potential which will induce quantum symmetry breaking, and it has Yukawa couplings, except for the remark that Shri made, that it is a U1, it has U1 anomaly. We have not discussed gauge anomalies, so I will not make too much of a remark on that, but if any of you understand that, is that this gauge symmetry that we have here is radiatively broken. Because of chiral anomalies. There is a chiral current. You have the gamma 5 current, right? You know gamma 5 invariance, I think we discussed in some context. That invariance, classically this theory has that invariance, quantum mechanically that invariance is not there. You could cure this invariance, in non-invariance, by adding another left-handed fermion to this theory, some psi chi L, with charge instead of plus 1 unit for this, minus 1 unit for that. If you do that, then it will become anomaly-free theory, which means chiral current would be conserved in that theory. That's what happens in electroweak theory. Electroweak theory, chiral conservation is assured because the hypercharge in electroweak theory comes in such a way that is distributed over various fermions in the theory in such a way that the total U1 charge is 0. An anomaly is proportional, chiral current anomaly is proportional to U1 charge. So here what I said is that you could add another fermion with a U1 charge which is opposite of this fermion. But that's not going to change the discussion that we are going to develop, so let me not worry about that. Okay? Is that okay? So this Lagrangian has almost all features except for anomaly of standard model electroweak theory. Now, what are the various parameters in this theory? There is electromagnetic coupling E, there is 4 fermion coupling lambda, there is Yukawa coupling Y. So 3 couplings. And there is a dimensionful parameter mu square. And the sign of the mass term we have chosen is the wrong sign. Wrong sign in the sense that it is with this sign, this potential induces symmetry breaking. If it was minus, then it would not induce symmetry breaking. It is with plus sign here that it induces symmetry breaking. So now let me look at the couplings. The electromagnetic E coupling and hypercharge. Sorry, the Yukawa coupling, electromagnetic coupling and Yukawa coupling. You can put them to 0. If you put them to 0, what does that mean? That means there is no electromagnetic interaction. There is no Yukawa interaction. Then that is enhanced symmetry. That's enhanced symmetry because the particle type is conserved. A fermion is always a fermion, never becomes a fermion plus a gauge field because it never emits a gauge field. Okay? Similarly, because Yukawa couplings are absent in Y going to 0 limit, fermion never becomes a scalar plus fermion because there is no emission of a scalar field by a fermion, or there is no process where a scalar field decays into a fermion left-handed and a fermion right. So these are, so enhances symmetry. And hence natural. What about the 5-4 coupling? The self-coupling. Lambda going to 0, if I make lambda going to 0, self-interaction goes away. But unlike the example which we discussed yesterday, which was only of scalar fields, lambda here is not really a natural coupling. Why? Is that if I started with lambda going to 0 theory, which means I had no such term, radiatively I will generate a 5-4 interaction. How do I do that? Simple example. So in this limit, look at the following 4-point function of phi's. Phi is dotted line and gauge field, dotted line, dotted line, dotted line. So this is a complex scalar field, so there is an arrow on it. So one of them is phi star, the other one is phi, phi star, phi. So there is this kind of a diagram at one loop, which comes from the vertex. This is an E, 2 A's and 2 phi's. Clear? 2 A's and phi star phi. That is this vertex. And then I close it. So this one is ordered, this one has a strength E, or in fact E square, right? No, E square, right? Because there is one E here and one E here. So this will give me, even though I had a tree level lambda equal to 0, at one loop level, I'll have an effective potential, a term in the one loop effective potential, which will be e to the 4, e square and e square here, and some numbers here times phi star phi square. And when I put the propagators here and do the integration over the internal loop, these are two propagators, two gauge field propagators, which will go like by 1 by k square each one of them. So I have a total strength of 1 by k4 integral dk4, which is log divergent. So something of this kind. So even if I did not have lambda 4, the phi 4 interaction at the tree level, if I in this limit, at one loop level I will generate it, and that will have a strength of the order of E4. So even if I have no lambda 4 at the tree level, I'll have it at one loop level. So what does that mean? At one loop level, the value of lambda is of the order of e to the 4. And some numbers, some coefficients here, some logs here. So which means this lambda, if this was non-zero but small, some, would get a correction of this order. So that tells me that lambda, when it's non-zero, it cannot be larger than this one, because if it's larger than this one, it will get destabilized. So it's if it is much smaller than this one, it will get destabilized because if it's large. But anyway, this is not really a very large number. This is E square is Normally you have e square by 16 pi square, right? That kind of a number. So which is of the order of 1 by 100, so it's 1 by 100 square. So this is 10 to the minus 4. So what it tells me is that this lambda, if it was not 0, can be of order this. So lambda effective has to be of the order or of this of order e to the 4 or larger than that, because then this correction would be small. But if it is smaller, significantly smaller than that, then this is essentially its value. So now this is not the only contribution. This was gauge field loop. Let me calculate from here another diagram. Another diagram is here is a fermion, external line scalar field and a fermion loop. So phi star, phi, phi star, phi. At one loop I have this kind of diagram also. That is also going to give me an effective action, and this is Yukawa coupling. So this is order y, this is order y, this is order y, this is order y. So this is y to the 4. And then I have these internal loop integration. I have 4 fermion propagators. Each is of the order of 1 by k slash, which is dimensionally 1 to the k to the 4, integral d4k. So that's again log divergent. So this tells me again lambda effective, if this was 0, would be order y to the 4. So put together, lambda effective would be some number times order e to the 4 plus some number times order e y to the 4. So the values of the lambda and these have to be roughly of the same order. So for lambda to be natural, the possible values that I put for them should be controlled by these couplings. Is that clear? Okay, that's for the couplings. Now, what about the mass dimension, the parameter with mass dimension, mu? So a parameter mu with mass dimension 1 is special. How is it special? Now let me look at the potential. What is the potential that we have in this theory? V phi is mu square phi star phi minus, potential is the minus of that, so minus plus square. This whole thing is minus potential. Lagrangian density is kinetic energy minus potential. So this is minus potential. In order to study the spontaneous breakdown of this theory, what I need to find out is what is the minimum of this potential. So minimum of the potential. How do I do that? Just take the first derivative and put it equal to 0. So first derivative with respect to phi, let me say phi star is mu phi plus lambda by 2 phi star phi phi. Oh, 2 upstairs, right? And so minimum of the potential will be when this object is 0 or this object is 0. And that tells me is that phi star phi vacuum or minimum value is mu square by 2 lambda. And let me give this a name as v square by 2, where v square is mu square by lambda. Now, in order to study the spectrum of this theory, what do? I expand around this vacuum. And this vacuum is in fact a ring. See, if I draw the potential of this potential is something like this. So a real value of phi, imaginary value of phi is something like this, where this is so this is real phi, and let's say imaginary phi is somewhere here, so it's something like where there's a ring here and there's a ring here, and this object is phi star phi vacuum, square root of that, and which is v by root 2, the diameter. The radius of this ring is, this is 1. So this is what the potential is like. So the spectrum is, you make an expansion around this vacuum by writing phi to be v plus h square root 2 times some phase. So you make an expansion of, write phi as 1 by square root v, v is the vacuum expectation value, plus fluctuation around the vacuum expectation value and a phase. Then the minimum of phi phi dagger is v square by 2. And the minimum vacuum value of h is 0. So This is a complex scalar field, so it has two independent components. One of them is H, which is real, and one is sigma. The sigma phase is what is the Goldstone boson, Nambu-Goldstone field, and this is what which will disappear because of its coupling to the gauge field, become the longitudinal component of the gauge field, and will be left with a real scalar field, which will be a physical field, equivalent of Higgs field, Higgs particle in this theory. So let me write now this potential, expand this potential V phi phi star by using this object. It is mu square by 2 V plus H square plus lambda by 4 V plus H to the 4. And expand this out. What do you get? What you get is minus lambda V4 by 2 plus lambda V square H square plus lambda VHQ plus lambda by 4 H4. Remember, V is V square is mu square by lambda. That's what we just expand this out. This is what you get. There is no linear H term. There is no linear H term because we are expanding around the minimum. The linear H term, the coefficient of linear H term will cancel out because V is the minimum of the potential. But what do you have? We have a lambda V square H square term. Now this is the correct sign for a mass term as opposed to this one. So this is a physical field with mass given by this object. This is half m square. So what we have is a physical field, Higgs field. So Higgs particle of this theory with mass mh, which is square root of 2 times lambda V square. That is square root 2 lambda V. So this is a physical field. There is a physical particle with this mass in this theory, proportional to the vacuum expectation value, times 4 scalar field coupling here, square root of the twice 4 scalar 5-4 coupling. Now let me make the same expansion in this term. Right, phi expanded around the vacuum. What do I get here? So I have a term there. Let me rewrite it down. I e a mu square phi star phi. This term times this term, and there is I and minus I, so that goes away. There's a plus I here. There's a minus I here. So this term. And this term I can write now as E square a mu times V plus H square divided by 2, and which is E square a mu V square plus 2 VH plus H square. And from here, this is the mass term for the gauge field. So I have a gauge field, massive gauge field, with mass, this is the m square. E square times V square is m square, so mass is E times V. So a gauge field with mass proportional to the vacuum expectation value times the gauge coupling. So I have now a spontaneously broken gauge theory. Now let me look at the Yukawa coupling here. So Yukawa coupling, what do I have? Y phi psi L bar psi r, and that is equal to y by square root 2 V plus h exponential I sigma psi L bar psi r. I sigma psi bar L, let me call it psi prime. I rubbed off. No, it's here, already here. Where psi L is exponential I sigma psi L prime. Huh? The psi L prime here is I exponential I sigma plus. Yeah, no, minus, because bar. There's a bar here, so that will convert into plus, and that's what I have here. Now, what is this psi prime? Psi prime is the gauge rotated psi. Is that clear? So I gauge rotate psi into a new psi, and then look at this, the first term, this is the mass term for fermion. So then the mass, fermion mass is now m psi is y v by square root 2.
So the psi L and psi r are like, they don't have the same overall phase of how we say. Shouldn't you also perform a similar gauge rotation on psi r as well, before you can identify that as the mass turn?
No, because psi r is neutral under gauge transformation. It doesn't change. See, we have not put any coupling of this kind for psi r. Oh, I'm sorry, I didn't write this psi r term. I should have put this term. I didn't write it. I have it in my notes or not? Yeah, I have it here. So what do I have? Let me summarize what I have done. I have expanded this theory around the vacuum and worked up the spectrum of this theory. So what do we have? We have a spontaneous breakdown of U1 gauge theory with the spectrum that I have Higgs field of mass square root 2 lambda times V, gauge field E times V, and fermion field of y root 2 times v. And v is the vacuum expectation value of the potential of the scalar field. So all the masses are proportional to the vacuum expectation value. And let me write v explicitly here is mu square by lambda square root. So in this theory, if you want to discuss the naturalness properties of mass parameter mu, that is as good as studying the naturalness values of naturalness properties of vacuum expectation value. So now, is there a symmetry when v goes to 0 or equivalently mu goes to 0? When v goes to 0, Higgs mass goes to 0, gauge field mass goes to 0, fermion mass goes to 0. So all mass going to 0, there is clearly an enhancement of symmetry. Classically, there is enhancement of symmetry. And what is the symmetry? In fact, there are three symmetries here. Scale invariance, there are no mass in the theory, so there is a scale invariance. Not only that, gauge invariance, because there is no spontaneous breakdown in symmetry if mu is 0. Gauge field is massless. And then there is third symmetry. Fermion mass is 0, chiral symmetry, which is the left-handed fermions and right-handed fermions are separately conserved So what do we have? We do have enhancements of symmetry. But is this a quantum symmetry? Is this do we have this enhancement in quantum theory? Classically, that's true. At the tree level, that's true. But classically, quantum mechanically, is that true? So if I started with v to be 0, which is mu to be 0, then classically I will have all these three invariances. Because when mu is 0, v is 0, there is no spontaneous breakdown of symmetry. This gauge field is still a massless field. Okay? But these are all classical statements, tree level statements. Are these statements true at quantum level? They are not true at quantum level. Quantum level, these invariances are broken. Have any one of you studied what is known as Kohnemann-Weinberg mechanism of radiative symmetry breaking in a scalar field theory? No. Anyway, we'll not study it in that way, but I'll indicate a proof of that while we go around. And this is so. First thing is scale invariance is broken. I said it earlier because quantum radiative corrections break scale invariance generically because they introduce a cutoff, which is a dimensional object, mass dimensions. Anything that any dimensional parameter introduced in a theory breaks scale invariance. But not only that, even the gauge invariance is broken radiatively. Gauge invariance is broken radiatively. And that is called Kohnemann-Weinberg mechanism. This Weinberg is not the super famous Steven Weinberg. This is another Weinberg, not that much famous, Eric Weinberg. And what does this tell you? This mechanism tells you is that even if you have a potential with scalar fields which has a vacuum expectation value 0, radiatively vacuum expectation value gets generated and therefore symmetry gets broken. So even if we had V equal to 0 at the T level, at the quantum level, let's say one loop level, V will become non-zero. And if V become non-zero, this whole exercise tells you gauge symmetry will be spontaneously broken. We started with mu equal to 0, let's say. No, we started with the positive here, and then what we did is that we found this symmetry breaking. Now I'm talking about if I have a theory where mu square is 0, then classically vacuum expectation value is 0. In that theory, with no such term, a term of this kind will be generated with this sign. Yes. Let me indicate how that happens. Now let me not take V to be 0, but look at this theory as it is. Right? Expanded around, I think I have all the terms that I need. Yes. Yeah. So expanded on, potentially expanded here. These interaction pieces are expanded here. I mean, phi square pieces with this are expanded here, and then Yukawa is expanded here. There are also mixed terms, derivative of phi here with a's. So there are those terms also there, which I have not written there, but whatever, see, you keep the track of that. And look at the following object. At one loop level, this interaction, h to the 4 interaction, h to the cube interaction, is going to generate a diagram of this kind for me. One loop is scalar field external line, a single scalar field line. If I wrote a functional integral and did the standard things that in the early lectures we learned how to do that, find out Green's functions from here, there will be a Green's function corresponding to this diagram with one external leg H, and that will come from an interaction which is this.
So you're not doing this in the V equal to 0.
You may do it at B equal to 0 or non-zero also. So okay. Yeah. Yes, you do. So let me do it V non-equal, V not equal to 0. Yes. Huh? So take V not equal to 0.
You start with mu square equal to 0, but V not.
No, I'm starting with mu square, mu non-zero and V non-zero. Let me start in this theory itself.
I thought you wanted to show that V square equal
No, I'll show you, but let me do this calculation. At the end of this calculation, you'll read off how to go to V equal to 0. If you do it directly from, in that case, this becomes a little more subtle. So let me do it, put V first here and then calculate and take then V equal to 0 limit. So this is what it is, right? And this coupling from there is order V lambda, right? This is an H loop, this is an external line H. You also have diagrams from here. This vertex. One external line H and one gauge field. And the strength of that object is V times E square. So this coupling strength is E square times V. You also have a similar kind of a vortex here. One edge and two fermions. And strength of that coupling is Yukawa by root 2. Clear? So what would these diagrams mean? Now first let me write down what are these diagrams. Each one of them has one loop. A scalar loop is propagator 1 by k square minus m square. Propagator d4k over k square minus m square. In the Euclidean way of, otherwise it will be what, plus m plus I epsilon. This is chordically divergent. So this answer would be some number lambda times the cutoff. Capital lambda is the cutoff. This is the gauge field. So this is also 1 by k square propagator. So this is now E square V lambda square, chordically divergent. This one is order y by root 2, and if you do it a little more carefully, if I take care of the masses, it will be mass times lambda square, fermion mass times lambda square, and that is equal to fermion mass is order y, so this is order y square by lambda square, because fermion times v. Fermion mass is y times v. So all these diagrams are chordically divergent and they will come give you contributions of this kind: V times lambda coupling times the cutoff square, E square times V, and Y square times V lambda square. So which means this will give you a coupling, an effective one loop coupling of the kind, besides other terms. We have lambda V H cube from the tree level, E square V H square, no, so lambda square V square. This is the tree level, this term, and plus that term, let me not, or maybe let me not keep track of that, plus one loop term, which is some numerical coefficient P times V lambda plus Q times E square V minus R times Y square V times lambda square times H. So some numerical coefficient here times this object V lambda times lambda square. Some numerical coefficient Q, some numerical coefficient R from this diagram, and I put a minus sign here because fermion loop must have a minus sign, times H, the external line. This is the one point, one loop effective contribution to the Higgs potential. Is that clear? H square is this is the tree, this is the tree level pieces, and these are one loop level. And then of course also, sorry, that we have put in lambda, yes. Huh? So this is what we have. Let me rewrite that: effective Higgs potential is this whole thing. Let me call this, give it a name, D. In fact, one more thing, I should put a minus sign here. Why do I put a minus sign there? In Euclidean action is exponential minus s, minus. So when I put it in the effective action, that minus is to be taken out. But some no coefficient here, some coefficient here, some coefficient here. And now let me rewrite this as lambda V square H square term was there a lambda? Oh, sorry, this is not lambda square, lambda V square. That's what he was pointing out. Yes. So this is lambda V square. So this term minus D times H. This whole thing I am calling D. Plus higher order terms, H cube, H4. This is what my effective potential has become, one loop effective potential. with a linear term H being generated radiatively. There are also terms which are generated quadratic terms here radiatively. I will come to that discussion later, but at this level I have this. Now, in order to interpret the mass for this field H, what do I have to do? I rediagonalize this potential. How do I rediagonalize? I rediagonalize this potential as writing lambda V square H square minus D by 2 lambda. Why did I put 2 here? Yeah, 2 lambda V square H square. Yes. There are H cube, no, I put H cube here. There are H cube. For the discussion, these are the 2 terms that are relevant. There are H cube, H4 terms. Okay. I can absorb this linear term by writing these 2 terms like this. The square of that gives me precisely this linear term, H square this. And there is the square of this object, which is a constant. Is that clear? But what has happened? Now at one loop my physical field is H prime with mass lambda V. Mass square is lambda V square, twice lambda V square. But what has happened is that H prime, the vacuum expectation value of H prime is vacuum expectation value of this object times vacuum expectation value is or maybe minus, right? This object. Something's not right. D has to be this should be positive.
Is the minus really there? What do you put?
Well, it also depends. I have not checked on these coefficients PQR, right? These things.
This minus, if you put it in the Lagrangian, it's not there, right?
Yeah, no, but this see this overall coefficient
Yeah.
can still be. I mean, these things can still be negative, which means yes. And essentially, is that this object must beat other signs. And that's what I think happens in the theory. You must have enough number of fermions that this beats this sign, so that U D is positive. So what you do is that this should be D should be in this way. I have written D should be negative, so that this object is positive.
Now, what was your argument for the overall minus sign there?
overall minus sign because minus exponential minus s has minus sign. But maybe no, that's not true because I'm writing potential, right? So potential already has, because this is also minus, this is also minus, so I think I should put plus here, right? Yeah, yeah, I think that's what it is. Yes, yes. So then this would be plus here, plus, so this is plus. Okay. So now what is the one loop effective action for the scalar field? One loop effective action for the scalar field is, or is that or no? Slow, something is not right. What should it be? Is b by root 2 plus this object. Yes. Yes. So that's what. Now, this is one loop effective potential. One loop. Earlier it was only this much because h expectation value was 0. Now, this is phi is vacuum, the tree level vacuum plus the expectation value of h prime. So that is this object. So and that is b by root 2, and d was that number p lambda plus q e square minus r y square v lambda square divided by v square. Do I have the right v's? No, sorry. This is one loop is v square by this, and it is so this is square root 2 square. This is what it is, that's right. And this is v square by 2, and expand it out and gives me the root 2 p lambda plus q e square r y square. This is 1 by v times v, v will go away, and then I'll be left with lambda square plus higher order terms. The phi dot, this was the vacuum expectation value at the tree level. Now at one loop level, because this object is added to it, this is what it is. Square of that is this. Expand the square, and this next order term is lambda square e square y4 square. So that's high order in coupling. So keep the leading order term, and that's this. Now what does that mean? That means v square effective one loop by 2 is v square tree level by 2, because this will call v square effective, vacuum expectation value effective, plus some number p prime lambda plus q prime e square minus r prime y square lambda square. Is that clear? This object we call the effective one loop expectation value by 2, that is this term, and this p prime is this root, some of this number by absorbed here, this absorbed here, this absorbed. So it's some number times lambda plus some number times e square, some number times and lambda square, plus higher order term corrections of lambda square, e to the 4, y to the 4, they are higher order. Now this is essentially what is Coleman-Weinberg mechanism. Because if I take V to be 0 here, even when V is 0, V effective is not 0. Is that clear? Radiatively, even if I had started with a vacuum expectation value 0, I would have generated vacuum expectation value, which would be quadratically divergent. So, quantum radiative corrections break gauge symmetry even when it is exact at tree level. Is that clear? And when V is non-zero, this is the correction, radiative correction to the V. And if V is 100 GeV square, that's what standard model V is, then, and if the physical cutoff of the theory is large, this is a very large correction to the vacuum expectation value. Is that clear? We have essentially derived Weinberg-Coleman mechanism. This is precisely what Weinberg-Coleman mechanism is. Radiatively you can generate symmetry breaking. Now this is a radiatively vacuum expectation value has been generated, and through vacuum expectation value then there are, which is quadratically divergent, there are corrections to quadratically divergent corrections to all other masses of the theory, because all other masses were proportional to vacuum expectation value. The gauge field mass, fermion mass. So if this correction is unstable, radiatively unstable, and the vacuum expectation value is unstable, all masses are unstable. Of course, I didn't. In addition to this vacuum expectation value, there are other corrections to the masses. Let me just indicate them. If you look at Gautam Bhattacharya's review, or also the lecture notes on supersymmetry that I circulated earlier, Gautam Bhattacharya has written a short small write-up as an exercises in that school where I taught. He had done that. There he has identified exactly the kind of terms which give large corrections in electroweak theory. He's identified one large correction, which is essentially a top loop, which is fermion loop. Alone he has given you. The top loop introduces large corrections to the vacuum to the Higgs mass. Now, in addition to the vacuum expectation value, there are other corrections to Higgs mass, and they come from the diagrams. From the same diagrams, we take the Higgs line, 2-point line. The mass corrections are from 2-point functions. How many 2-point functions can I construct there? This is a 1 2-point function at one loop. This is another one. These are essentially due to this shift in the vacuum expectation value. Then in addition to that, you also have corrections like from, this is the h to the 4 interaction. We rub that off, or maybe that's still there, yes. H to the 4 interaction. This is order lambda. Then we have this interaction. 2 A's and h square. That will give you a diagram of this kind. Then we have this 3.2 fermions and 1 Higgs. These are additional. These are all additional one loop effects. And now look at them. All of them are chordally divergent. This we already seen. They are chordally divergent. This is chordally divergent. This is chordally divergent. This is also chordally divergent. So all these things give you chordally divergent corrections to Higgs mass. So generically, one loop correction, if I write one loop correction to be delta mh square, that is from this kind of a coupling is total is some coupling times the cutoff square, because they're all chordally divergent. Where alpha is some number, or alpha square, and alpha is some number of some numerical a times lambda plus b times e square times c times y square. This is y square, this is e square, this is y, this is y, and generally 16 pi square is the number you get here, and some numerical factors a, b, c. So the point is that Higgs mass, one loop correction, is like this. So we have vacuum expectation gets renormalized by gets corrections which are chordally divergent. Vacuum expectation is scalar. Vacuum expectation is scalar field. Higgs mass gets chordally divergent corrections, and through vacuum expectation value, gauge field gets chordally divergent corrections. Fermion mass gets chordally divergent corrections. Means all masses get chordally divergent corrections. that is the moral of the story. All masses get orderly divergent corrections, mass squares. How long should we go? 4:15, 5 minutes. Okay. So this is what we have. So what does this mean? And okay, so this is true for this U1 theory that we discussed. And since this U1 theory is mimicking exactly what the Stennell model properties are, this is also true for electroweak Stennell model, except that the calculation will be a little more cumbersome there. But generically, they are the same structure. So in electroweak theory, one loop corrections to Higgs mass square is of the order of alpha times lambda square. One thing I want you to notice, when we discussed yesterday QED, which was theory of gauge field and fermions, no elementary scalar fields. There, we said the fermion mass is a natural parameter, because if we did the radiative corrections, calculate radiative corrections, the electron mass, it also had only logarithmic divergences. And with mass going to 0 limit, we had the chiral invariance. Here, we have fermion and we have their masses, but mass going to 0 limit is not a chiral invariance, unlike QED. And the reason is that in this theory, we are giving mass to the fermion through a vacuum expectation value of the scalar field, the Yukawa coupling. That vacuum expectation value itself is not radiatively stable. Is that clear? So sometimes people make this argument is that fermions are protected by chiral symmetry, fermion mass is protected by chiral symmetry, therefore it should not get radiative corrections, which are large. That is true only if there are no elementary scalar fields in your theory, which are coupled to fermions. If you have elementary scalar fields coupled to fermions, that statement is not true. And this is what we see here. Same way we said, the same way one could talk about that M, the gauge field mass going to 0 could be a natural parameter, because gauge field mass going to 0 means gauge invariance. So there is enhancement of symmetry. So does that mean, but that is also not true always. Why that's not true? If the gauge field is getting mass like we have here in Spondon symmetry breaking through a vacuum expectation value, then the gauge field mass is also protected as much as the vacuum expectation value is protected. And since vacuum expectation value is not protected for scalar fields, gauge field mass is not protected. So the gauge field mass, even if you had no gauge field mass in the tree at the tree level, radiatively you will generate, and you will generate which would be chordally divergence if there are elementary scalar fields in your theory. So elementary scalar fields make all mass parameters that the elementary scalar fields couple to unnatural. Okay. So that's one observation. Second is now, what does this mean? In that Higgs field, mass correction is some number alpha, which is coupling, times lambda square. Now, if I require that this correction should not be larger than the tree level correction. So, what is the mass? Mass of Higgs field is expected to be around 100 GeV. And if the results that have been announced are really will get really confirmed at LHC recently, it's about 121 GeV. If that is really what they have seen is Higgs, then it's 100. But the vacuum expectation value is supposed to be around 100 GeV, and Higgs mass is supposed to be around 100 GeV. Now, if I want the correction also to be not larger than this, so you take the correction also, let's say 100 GeV square, not larger than that. What does that tell me? That tells me lambda square, which is of the order of delta m square by alpha. Delta m square I want to be 100 GeV square. And alpha is typical gauge coupling square. And typical electroweak gauge coupling square with E square divided by 16 pi square, those numerical factors, that is generally of the order of 1 by 100. So, alpha is order 1 by 100. So, this 1 by alpha is order 100. So, this number is therefore of the order 1000 GeV square. What does that mean? That means I cannot have a physical mass in electroweak theory which is larger than 1000 GeV, because if I have, then that will give me corrections to Higgs mass which will be larger than 100 GeV. So, that is the naturalness breakdown scale for electroweak standard model is thousand GeV, that is 1 TeV. The electroweak theory will cease to be natural for scales larger than 1 TeV. So, that makes this number 1 TeV special. Everybody talks about physics beyond standard model 1 TeV physics, and this is the reason for that. Why is one talking about physics beyond 1 as 1 TeV as a very special scale? We are not very careful about 1 TeV. It could be 1, 2 TeV, 3 TeV, but it's made only an order of magnitude assessment. 1.5 TeV. Something out there is up to which the standard model is valid. Beyond that, some new physics has to be there. Is that clear? 1 TeV, what is so special about 1 TeV? Is because 1 TeV is the naturalist breakdown scale for electroweak theory. There are other reasons also for 1 TeV, but from this perspective, 1 TeV is special because of the nature of electroweak theory. So maybe we'll pick up from here tomorrow, huh?
That means alpha is the order of 1 by 100. And from here, 1 by
No, that's the physical electroweak coupling. G square by 16 pi square. That's a physical object input. ABC has some numerical numbers, they are small numbers, order 1 numbers. 1 by 10, 1 by 2. So that's the one, you see, I'm saying this is, when I say 1 TeV, this is not so sophisticated number, but it cannot be 100 TeV. It cannot be even 10 TeV, just 1 TeV, 1.5 TeV or 2 TeV, that, around that range. Okay. So we'll pick it up from here tomorrow.